Hi everybody, we are going to start in with Unit 5, Section 7, which is some theorems about definite integrals. The first one we're going to look at is, we've got this function f of x over here, and what happens if we were to find the integral from a to c under f of x, and then add that to the integral from c to b. So from a to c would be this area right here. And then from C to B would be this area. And so a shortcut way to deal with this would be to say that if we wanted to go from A to C and then from C to B, that we would end up going from A to B. Quick note, C does not have to be between A and B. C could be over here or back here. As long as you go from A to C and then from C to B, those numbers will account for each other. Okay, so it's fine if C is not between A and B. Example 2, from A to A. So if we're looking at from A to A, we're really seeing what happens under a single point on that integral. And in mathematics, the only way we have to deal with what the area is of this little sliver right here that has absolutely no width is to say that that area in and of itself is 0. So if you're going from a starting point and an ending point that are the same, then we will assume that those two things are 0. For number 3, if we wanted to go from B to A, so kind of switch it up and start with a point that's further to the right and then go back to a point that's to the left of that. We could think about the exact same way as from A to B, but with a negative. So we take that opposite area if we account for going backwards. So if I went from, say, 5 back to 2, so if I went from 5 to 2 instead of 2 to 5, I would just call that area negative instead. In number 4, we're going to look at what happens if we add two integrals together or subtract two integrals together. And luckily for us, it works out really nicely, exactly the way that we would expect it to. So if you're doing the sum of two integrals, then you are free to split them into two pieces. And you can deal with each of them separately. In number 5, we're going to look at what happens if we have a constant in front of our integral. So what if we have an integral that's multiplied by a number, 1 or 2 or 3? And the way we're going to deal with that is we're going to put that number in front, and then we're going to evaluate the integral. So if you have a number like a 2 in front, you can just stick that in front, and that will we can evaluate our integral after that. Okay. So let's look at what this looks like in a few more examples. So here we are. And we've got some information there. We know that the integral from a to b of f of x is 9. From b to c is negative 7. And from a to b of f of x squared is 36. And a to b of g of x is negative 2. Use this information to calculate each of the following. So we're going to first look at the integral from a to c of f of x. And we don't know that. That wasn't one of the ones we were given, but we were told that a to b was 9 and b to c was 7. And so if we want to think of b as our little connector between these two, then we can use this first rule where we have a little connector here that connects those two integrals. So we can think of that b as drawing those two values together. So we can say this is the same as the integral from a to b plus the integral from b to c. And we know that the integral from a to b has value of 9 and b to c has value of negative 7. And so we know this whole thing is going to have to equal negative 2. let's look at, so that was choice A. Let's look at B now. The integral from a to b of f of x, that whole thing squared, minus, and then we got a big parenthesis, integral from a to b of f of x dx, and then that squared. So the first thing we're going to deal with is that we've got this a to b that we need to find the value of. And so we know that from up here of f of x squared, that's going to be 36. So I'm just going to lump that guy in there. And then we're going to look at a to b of f of x. I'm going to ignore the fact that this is squared at first, and I'm going to deal with this inside portion right here. And so we know the integral from a to b of f of x, we found that here, is 9. But we still need to square that. So I'm going to evaluate this inside part first, and we'll get 36 minus 81. And that 36 minus 81, let's see, that would be 4 to get up to 40. And so we're looking at negative 44, I believe. And now let's look at C, which is this guy. I might put him over here so we have a little more room. So the integral from a to b of 2f of x minus g of x. So for this one, we're going to use the last couple rules that we have, which involve the adding and subtracting, and then if we have a constant in front. So I'm going to split this into some pieces. First, I'm going to go from a to b of 2f of x dx minus the integral from a to b of g of x dx. That's just splitting that integral into two pieces. And then I'm going to take this 2 that I had here, and I'm going to put them in front. Because remember, if we have a constant, that we are allowed to put that value in front. And then I'm going to calculate each of these little bits. So the integral from a to b, we've done that several times, that's 9. And let's see, the integral from a to b of g of x, that's negative 2. Don't forget that we're subtracting a negative 2 here. This value is negative 2, and then we still have a minus from there. So we're going to end up with 18 plus 2, which would give us 20. And so last, we're going to look at what happens when we try to find the area between two graphs. And for now, you guys only know how to evaluate an integral when you have in front of you a calculator. So we're going to have a calculator for these. So let me just pull up my calculator here so you can have a look at what these graphs might look like. I'm going to graph g of x and f of x. And we should be able to see that those two things, those two graphs, create a little space between them. And we want to try to find the area of that. So I'm going to go over here to my graph. And I'm going to put in f as, where it was, negative x squared plus 4x minus 1. Sorry, I'm slow on my computer there. Okay, so there's f of x. And then I'm going to put g of x in as f2. And so that was x squared minus 4x plus 5. X squared minus 4x plus 5. And that graph comes in red. Okay. So if you look, we've got f and we've got g. And what we're trying to find is the area of the region that is bound between them. So let me just pull up my thing here. Whoops. So I'm trying to find the area of this region right here. It's like a little football shape that we've got between there. Okay. So when we're dealing with that region, the first thing we might want to know is, what are these little points right here of intersection? And so if you look on your calculator, that's the place where those two graphs are going to equal each other. And so we could find that either by setting these two graphs equal to each other if we wanted, or by using the intersect feature on our calculator. So I'm going to go to Menu, Analyze Graph intersection. And I'm looking between here and here. And they're going to tell me that this point is 1, 2. Do it again. Here to here, and that point is 3, 2. You also could have found that by hand if you wanted, by setting those two graphs equal to each other. That's solving a quadratic system of two equations, which you did some last year. Oops. So I'm interested in this shape right here. And if we're going to find that, then we know that it's this space between x equals 1 and x equals 3. But here's the thing. All we've ever found so far is the area underneath of one curve when it went all the way to the x-axis. So for instance, if I wanted to find the area of this blue curve, like from 1 to 3, it would be all of this, right? That would be the integral from 1 to 3 under f of x. But that's not what I want. I want just that little green portion. So what I need to do is I need to subtract out all this stuff down here that I don't need. Well, that happens to be the area from 1 to 3 under the second one I have, which is g of x, right? If I do the blue area minus the red area, I'll end up with that green portion that's left. And what we've got here is actually a formula that you're going to use quite often. If you want to find the area of a bounded region, let's get back here a slide. If you want to find the area of an enclosed space, then oftentimes it will be the integral from the intersection on the left and the right of the top curve minus the bottom curve, dx. So looking back here, not here, but here, you can see that I've got top curve minus bottom curve. I can combine that into one integral if I wanted. Integral from 1 to 3 of f of x minus g of x dx. By my integral rules, I can put things together just as well as I take them apart. So I'm going to do that over here on this other screen. So in this case, it's going to be my top curve. We go from 1 to 3. My top curve is negative x squared. Let me put that in blue because it was blue over there. Negative x squared plus 4x minus 1 minus, and my bottom curve is then going to be that g of x, x squared minus 4x plus 5. And this is something you can just put directly into your calculator to get your answer. Just put that right on in there. So we could go over here to menu. Oops, sorry, we need to be in the other screen. Okay. Menu, calculus, integral. We're going from 1 to 3. And my top curve was negative x squared, so I'm going to put parentheses around that. You guys are probably much faster at this part than I am. It's kind of hard to do it on your computer screen. Plus 4x minus 1 minus, I'm going to give me something, another set of parentheses. Those parentheses are really important. If you mess them up, you can end up subtracting not enough terms. So you have to be really careful. My g of x is minus 4x plus 5. And all that is dx, of course. You can enter, and it'll give you 8/3 as your answer. So that tells me this answer would be 8/3. Okay. So let's look at something similar in example 3 when we've got cosine and sine. You might even know what that graph looks like. Let's just go ahead and see if we can sketch it out from memory. We're going from 0 to 2 pi. So I'm going to do cosine in pink here. We know that cosine starts up at 1, goes down, and ends up back at 1 from 0 to 2 pi. And we know that sine of x is going to start at 0, go up, down, down, and up, okay? And so that's going to give us, if we're going from 0 to 2 pi, a lot of regions, really, the area enclosed by those two graphs. And so we've got kind of, I don't know, a lot of different stuff from 0 to 2 pi. So we've got some different sections. We've got this little guy over here. I'm going to color him red. We have this one. He's blue, right? And then we have this one, which is green. Okay, I had some technical difficulties before that stopped me in the middle of that example, but I think we're good now. So let's see if we can go ahead and finish this example up. We talked about the regions there that we had bounded, that red and blue and green one. And so if we look, where does the cosine equal the sine? Well, the cosine equals the sine at pi over 4. And then again at 5 pi over 4. That's a unit circle thing that we would need to know, where the cosine and the sine are equal to each other. And so what we've got here is 3 pieces, and you'll notice that top and bottom switch on this. And so if you look carefully, let's look at this red piece first here. So my first piece would go from 0 to pi over 4. And my top curve would be cosine. My bottom curve would be sine. Then I have another curve, that little blue area here, okay? And I'm going to call him, let's see, my top curve and my bottom curve. So my top curve is going to go from, we're going from pi over 4 to 5 pi over 4. And in this case, my top curve is that green one, which is going to be sine of x. And my pink curve will be below it. Does it matter that that graph dips below the x-axis? It actually doesn't. Sometimes that makes kids feel a little bit weird. But what's going to happen is, like for this portion here, this will be positive and this will be negative. But when I subtract this negative down here, it will add. So that distance between the two, area of enclosed regions, will always be positive. And so those will account for each other. So you can still use top curve minus bottom curve, even if you're below the x-axis. Top curve minus bottom curve will work. And so we're going to work out a similar situation over here for this part that's in green. We're going to go from 5 pi over 4 all the way up to 2 pi. And our top curve is cosine of x, and our bottom curve is sine of x. And so we're going to plug each of those into our calculator. Back here. Nope, that's not what I want. This guy. And here, let me just go over here. That faster. Stuff in. And I believe that if you plug all those things into your calculator, that you will end up with 5.7. You'll end up with 5.7. So that's our value here. You'll have to plug each of these in individually in your calculator. Okay. Okay, I had some technical difficulties before that stopped me in the middle of that example, but I think we're good now. So let's see if we can go ahead and finish this example up. We talked about the regions there that we had bounded, that red and blue and green one. And so if we look, where does the cosine equal the sine? Well, the cosine equals the sine at pi over 4. And then again at 5 pi over 4. That's a unit circle thing that we would need to know, where the cosine and the sine are equal to each other. And so what we've got here is 3 pieces, and you'll notice that top and bottom switch on this. And so if you look carefully, let's look at this red piece first here. So my first piece would go from 0 to pi over 4. And my top curve would be cosine. My bottom curve would be sine. Then I have another curve, that little blue area here. Okay, and I'm going to call him, let's see, my top curve and my bottom curve. So my top curve is going to go from, we're going from pi over 4 to 5 pi over 4. And in this case, my top curve is that green one, which is going to be sine of x. And my pink curve will be below it. Does it matter that that graph dips below the x-axis? It actually doesn't. Sometimes that makes kids feel a little bit weird. But what's going to happen is, like for this portion here, this will be positive and this will be negative. But when I subtract this negative down here, it will add. So that distance between the two, area of enclosed regions, will always be positive. And so those will account for each other. So you can still use top curve minus bottom curve, even if you're below the x-axis. Top curve minus bottom curve will work. And so we're going to work out a similar situation over here for this part that's in green. We're going to go from 5 pi over 4 all the way up to 2 pi. And our top curve is cosine of x, and our bottom curve is sine of x. And so we're going to plug each of those into our calculator. Back here. Nope, that's not what I want. This guy. And here, let me just go over here. That a little faster. Put all that stuff in. And I believe that if you plug all those things into your calculator, that you will end up with 5.7. You'll end up with 5.7. So that's our value here. You'll have to plug each of these in individually in your calculator.